We move to the vector, or what is commonly known as the cross product. It is so named because the product produces a vector. So if we have two vectors, u and v, in the three-dimensional space, then their vector product is determined by evaluating the determinant of a 3 by 3 matrix, where the first row will always be I, J, and K, which are our unit vectors in the directions of X, Y, and Z, respectively. And then the second row are the components of the first vector, and the third row are the components of the second vector. Please note that in this case we have U cross V, so the components of U go into the second row and the components of V go into the third row. Every time the first row will always be those unit vectors I, J, and K. Then the way I've evaluated here is always the standard form of evaluating a matrix, the determinant of a matrix, especially for a 3 by 3 matrix. In this case, we're using minors and cofactors. Please recall that the first column, or the first, should I say, yes, first column is positive, second column is negative, and the third column is positive in terms of cofactors. Remember, it's minus 1 to the power I plus j multiplied by mij, and we find mij by deleting the ith row and the ith column, and then determining the determinant of the remaining entries. That's what we did here. Minus 1 to the power 1 plus 1, because I is in the first row, first column, will give us a positive I, and then we delete the first column, first row. We are left with U2, U3, V2, V3 in our minor. And then we go to taking out J. Note that J is in the first row, second column. So our cofactor is minus 1 to the power I plus J. I is 1, J is 2. So that means it's negative 1 to the power 3. That is why we have a negative there, multiplying our J, which we took out from the second column. And then delete the second column, delete the first row, and then we are left with U1, V1, and U3, V3. Same with finding that positive K. When we take out K, K is in the first row, third column. So it will be negative 1 to the power I plus J. I is 1, J is 3. So that means negative 1 is to the power 4. That's why we have a positive sign. Multiplying K, delete the first row, delete the first column, that's the first row, third column, and then you are left with U1, V1, U2, V2 as your minor. And then it's easy then to evaluate the determinant of a 2 by 2 matrix. So it's U2, V3 minus V2, U3 in the first one. In the second one, U1, V3 minus V1, U3. And then the last one, it will be U1, V2 minus V1, U2. I hope we still remember how to evaluate the determinants of a 2 by 2 as well as a 3 by 3 matrix. Now let's find the cross product of u and v, given that u is I minus 2j plus k and v is 3I plus j minus 2k. Once again, recall the first row of that determinant is always the unit vectors I, j, and k, and then the components of the first vector, they go into the second row, and then the components of the last vector go into the third row. So we did the minors and cofactors to find this determinant, and we got 3I plus 5j plus 7k. Please check, and you may use also other methods to determine this determinant. Number 2, actually we're in B. Now we've been asked to evaluate V cross U. V cross U. Now V is the first vector and U is the second vector. So that means V and its components will go into the second row and U's components will go into the third row. Remember, the first row doesn't change. And then my V cross U gave me the negative 3I minus 5j minus 7k. Please confirm. And I hope you are noticing that in A we got U cross V equal to all those components being positive. Now V cross U gives us negative components. Therefore, U cross V is never equal to V cross U unless one of the vectors is a zero vector. Now let's go to the properties. But before we go to the properties, let's go to V cross V. V cross V now is just the same vector, and we are getting a zero vector. Note that V cross V is not equal to 0, but it is equal to a zero vector because it depicts the origin of a three-dimensional space, which is 0, 0, 0. Please check and see if we're going to get the same answer. Now we go to the properties of the vector product. All these three vectors, u, v, and w, are from a three-dimensional space, and k is a scalar. Then all these properties are true. There are 11 of them that I've picked up from different corollaries and theorems. Number 1, we've already proven it. U cross V is equal to the negative of V cross U. Immediately you interchange U and V. That means you're changing the direction. So U cross V is equal to the negative of V cross U. Now, number 2, number 3, and number 4 are exactly the same as the distributive laws that we saw in the scalar product or the dot product. And then number 5, U cross a zero vector is equal to a zero vector cross a U vector, which is equal to a zero vector. So this is the only time where we see that we can interchange two vectors as long as one of those vectors is a zero vector. Then we get a zero vector. And also our last example, U cross U, or a vector crossing itself, gives us a zero vector. And then let's go to the other properties. Number 7, distributivity again of the dot and the cross product. And then number 8, note that the cross product between two vectors is always orthogonal to both u and v, to both its vectors. Now, I need us to remember orthogonality, that means perpendicularity. In order for two vectors to be orthogonal or perpendicular, if vector A and vector B are perpendicular, that means the angle between them is 90 degrees. And therefore, it means vector A dot vector B will be equal to a zero scalar. Now, if we are saying U cross V is orthogonal to both U and V, we are saying the dot product between U cross V and U will give us a zero, and the dot product between U cross V and V will also give us a zero. Now, using the cross product, we are able to find the angle between U and V, which is now in this case, we're using sine theta instead of cos theta that we used for the dot product. And instead of U dot V, we have the length of U cross V. The length of U cross V, where there is U dot V, and then where there is cos theta, we use sine theta. Also, number 10, in order for us to prove that two vectors are parallel to each other, it means their cross product will be equal to a zero vector. Remember, for perpendicular, the dot product between those two vectors will be equal to 0. Here, the cross product will be equal to a zero vector if the two vectors are parallel to each other. Number 11, if you have a parallelogram that has got two adjacent sides as vectors u and v, then we are able to calculate the area of that particular parallelogram to be the length of the cross product. Here are some examples. Firstly, number 1 is requiring us to find the unit vector that is orthogonal to both u and v. Now, orthogonality, we know it could be the dot product, but then it's the dot product of what with what? In this case, we had one of the properties said u cross v is orthogonal to both u and v. Now, in this case, we are asked to find for the unit vector. So find u cross v for number 1, and then do the dot product between that u cross v with u, and then the dot product between u cross v and v, and see if you are going to get 0. And then again here, number 2, we've been asked for the area of the parallelogram with adjacent sides u and v. Area is the length of the cross product. That's what always gives us the area. So find the cross product between u and v, and then find the length of that cross product. Then it will give you the area. Again, here, prove that u cross v is orthogonal to both u and v. Now you're doing the dot product here. For number 1, I need you to remember the unit vector is always the vector divided by its length. So after finding the cross product between u and v, find the unit vector. So it will be u cross v divided by its length, and check using your calculators whether your answer is correct. Will that vector give you 1 or its length, will it give you 1? And then number 4, just find you V cross W first, and then do the dot product and see what you get. In our application of the vector product, we do the moment vector. So if F is applied on an object, that makes it to rotate about a fixed axis. Then the moment vector of the force about the origin is defined by M equal to the position vector R cross our force F. And note that R is the position vector from the origin to any point on the line of action of F. So we're always looking for the moment vector about the original point. So it has to be the initial point. We're looking for the moment about the initial point. As you can see here, it is always about the origin. And the position vector is applied from the origin to any point on the line of action of F. So we need to always make sure that the moment is calculated from the initial point of action of the force. It's R cross F. Here are some examples. First one, note that we are determining the moment about the origin O, and we've been given F and the position vector. Straightforward, R cross F, and we got the answer. You may confirm whether that answer is correct. Number 2, now we've been given 2 position vectors, A and B, and F is passing through point A in its line of action, and we are asked to find the moment of F about point B. That means, remember, we had said the moment of F always is sought about the original point. Hence, the position vector must be BA, B being the initial point and A being the final point. And if B is the initial and A the final point, our position vector R will then be equal to the terminal point minus the initial point. So it's A minus B. That is why our R is in that format, and then we calculate R cross F. Number 3, we've been given again position vectors R and S, and we are told F passes through R. Then we are asked to find the moment of F about point S. So that means point S is the initial point. So that means the position vector we're looking for is SR. S the initial and R the terminal or the final point. So that means we are going to have R minus S as our position vector, and then we do the cross product. Here, number 4, I would like you to find the angle between velocity and acceleration using the cross product, and then confirm if you're going to get the same answer when you've used the dot product. Number 5. F passes through the point A. You're supposed to determine the moment about point B. So it means B is the initial point and A is the terminal point. So please always remember the moment is always sought about the initial point. Straight to eigenvalues and eigenvectors, where we apply both our knowledge of vectors and our knowledge of matrices. Firstly, let's note that A is a square matrix, lambda is a scalar. Then we say that scalar is an eigenvalue of A if it satisfies that equation where vector x is a non-zero vector. Note that vector x can never be a zero vector. Then we'll call that vector, if that equation is satisfied, we'll call it an eigenvector of A corresponding to that particular lambda. And note, any matrix may have as many eigenvalues as possible. Let's do some examples. Firstly, we need to check the given vectors if they are eigenvectors of the matrix. So all we need to do is to check that equality. Remember, it's A multiplied by X equal to lambda multiplied by X. So I took the left-hand side, did the matrix multiplication. This is A and this is X. And then I got 2, 0. Took out the common factor and I got 2 into 1, 0. 1, 0 being the original a vector that we had. So that means it is an eigenvector because I was able to get the original vector again multiplied by a value which we call lambda. X2, we did exactly the same, and note that now lambda is equal to -1. Do the same for number 2. You may discover that some of the vectors that we've given you here are not eigenvectors, but you need to check. The equality A times that vector must give you a scalar times the original vector. Here are some other problems as well. How then do we calculate the eigenvalues and eigenvectors of a particular matrix? We start with the fact that, once again, we had said the matrix we're dealing with is a square matrix, and we start from the knowledge that Ax is equal to lambda x. Then we take lambda x to the left-hand side. Note that we are left with a zero vector because we realize that we are subtracting two matrices and their answer can never be just a constant zero. It has to be a vector. Then we are able to say that in order for us to calculate our eigenvectors, that equation must hold. But we have to substitute the corresponding eigenvalues in there so that we can be able to substitute eigenvector to get eigenvectors. Now note that in order for this equation to hold, we must know the values of the eigenvalues. But then how do we calculate the eigenvalues? We take the determinant of A minus lambda I and equate it to 0. And in that we get the characteristic equation, which we call the auxiliary equation. And then when we solve it, then we get the eigenvalues. the determinant of a minus lambda I is equal to 0 directly from that equation, because x can never be equal to 0. Therefore, the determinant of a minus lambda I is the only one that can be able to be equal to 0. Now let's do some examples and let's solve for the eigenvalues and eigenvectors. Once again, it has been stressed, in order for you to get eigenvectors, we need to solve the system of equations that will get from that equation a minus lambda I into x equal to a 0 vector, after substituting each eigenvalue into the system. Let's do some examples so that we can be able to understand what really is going on here. So the first things first, find the eigenvalues by using the determinant of a minus lambda I equal to 0. And then thereafter, use those eigenvalues, substitute them back into a minus lambda I, and then multiply that matrix with the vector x equated to vector 0. We've got these two examples here, A and B, where we're asked to find both eigenvalues and eigenvectors. Let's check the solutions that I've provided here. Number 1, the matrix is a 2 by 2 matrix, 6, 2, negative 3, and 1. So the first thing we write down, the determinant of a minus lambda I must be equal to 0. Then we get the determinant of a minus lambda I from our matrix A, and then find that determinant, solve it, and we get the auxiliary or the characteristic equation lambda squared minus 7 lambda plus 12 equal to 0. Factorize, and here are our eigenvalues. Lambda 1 equal to 3 and lambda 2 equal to 4. Now from here we have to find the eigenvectors corresponding to these eigenvalues. Lambda 1 equal to 3. We start there. We go back to that equation that I said we should use in order for us to get the eigenvectors. A minus lambda I times x equal to 0. Note that I've said here lambda 1, and here is vector x1, so that we understand that we're substituting lambda 1. So wherever there is lambda, I substituted lambda 1 so that we understand what is going on. In place of vector x, because this is a 2 by 2 matrix, we will have 2 unknowns, and our vector also on the right hand side will have 0 and 0. And then substitute lambda 1, which is equal to 3, and then we get that matrix form of our system. Change to equation form, solve simultaneously, and then what I got here was that both equations gave me x1 equal to x2. So the simplest way is to just let x2 be equal to 1, and then it would mean that x1 is equal to 1. So therefore vector x1 is 1, 1. Let's try and do for lambda 2 equal to 4. We do exactly the same. Lambda 2 equal to 4. Did that substitution in there. And then my matrix form of the equations is 2, negative 3, 2, negative 3, the constant matrix, x1, x2 as the variables, and equal to 0, 0. And then simultaneously I got x1 is equal to 3 over 2 x2. So simplifying the whole thing, I let again x2 be equal to 1, and therefore my x1 will be equal to 3 over 2. Therefore, in place of x1, I've got 3 over 2. In place of x2, I've got 1. To eliminate the fraction in my eigenvectors, I just multiplied by 2 both terms so that we get 3 and 2. Number 2. Here is a 3 by 3 matrix. Again, the determinant of A minus lambda I must be equal to 0. I'm hoping you are noticing that A minus lambda I is just changes the main diagonal entries of the original matrix A. Evaluating that determinant gave us that lambda 1 is equal to 1, lambda 2 equal to 5, and lambda 3 equal to negative 7. So when I substitute lambda 1 equal to 1, I got that equation. Get equations, all three equations from that. Let's see what we're going to get for the values of x1, x2, and x3. Those are the three equations that we got. Note that the last equation had just negative 8x3 equal to 0. And then it gave me x3 equal to 3. Note also that I wrote 0x1, 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 0x2. You will see why. From getting x3 equal to 0, you can just get it from equation 1 or equation 2. You will also get that x2 is equal to 0 when you substitute x3 to be 0. x2 will also be equal to 0. So these three equations gave us x2 equal to 0 and x3 equal to 0. And there is no way that we can be able to calculate x1. All we know is that 0 times x1 in all three equations is equal to 0. That's all we know. But that does not mean that x1 is equal to 0. 0 multiplied by any value of x1 is equal to 0. Hence, we say let x1 be equal to 1. It can be any real number. Therefore, our first eigenvector is 1, 0, 0. Remember, we could not just simply say x1 is equal to 0 because we did not calculate it. Where would we get the value x1 equal to 0 from? Also, you needed to keep in mind the eigenvector cannot be equal to 0, 0, 0. So we let x1 be equal to 1. Hence, our first eigenvector is 1, 0, 0. Now, please confirm for lambda 2 and for lambda 3 whether you're going to get these eigenvectors. Now, one thing that we need to note, eigenvalues may be real and distinct. As we have been, all our examples so far, we're getting real and distinct eigenvalues, or they may be complex, or they may be repeating. So in our next video, we'll be doing complex and repeating eigenvalues.